Welcome to a tutorial on the 8085 microprocessor, and we're gonna discuss here about its detailed architecture. So I'm just gonna bring a diagram of how it looks inside out. Okay, there you go. So that's quite a big picture that we got over here. So this entire diagram that you can see basically represents the internal architecture. So by internal architecture, I mean that what the how the things are inside the 8085 microprocessor chip. Okay, so as you can see that the 8085 is basically a microchip. Okay, and now inside that microchip we've got various different devices, okay, all embedded together to form what the 8085 microprocessor is actually. So let's just start with this part over here, that is the ALU, as you can see. So this part, that's the ALU, you can see over here, right over here. Okay, this is obviously the logical and mathematical control processing unit of the 8085 microprocessor. So that's why it's called ALU. ALU referring to arithmetic and logic unit. So I'm just gonna write that down over here. So there you go. Now ALU stands for arithmetic, okay, and logic unit, and this part actually performs all kinds of mathematical and logical operations on any input data. Okay, so that's how the ALU basically works, and whenever you just give any kind of data to the 8085 to process, it is actually done by this particular ALU unit that you've got over here. Okay, now apart from that, we also have the most important part over here, that is the register section. Okay, so this entire block that you got over here is actually the register section. So you know that there are 10 registers in total. Okay, so starting from, so if this is the register section, okay, we're talking about over here. So in the register section, the registers that mainly we discussed in the previous tutorial, they include the registers A, that's the accumulator. Okay, there you go, the accumulator or register A. Then we've got the flag register, okay, also known as register F. Alright, now apart from these two, we also have the general purpose registers, okay, so which include the B, C, okay, sorry there, I'm just gonna write that down, okay, side by side. Okay, B, C, D, E, H and L registers. Okay, and apart from all these, we've got two memory pointer registers. Okay, the one is basically the stack pointer. Okay, there you go, the stack pointer, also referred to as SP register in short, and also the program counter register. Okay, so there you go, program counter, also referred to in short as the PC register. Now you know that the stack pointer and program counter registers are both with 16-bit registers. Okay, they can hold 16-bit data. Actually, they hold the data of memory location, so they are used to hold the memory address data. Okay, I'm just gonna write that down over here. So it's a bit of recapitulation in this video, okay, as well as an introduction to what the inside of the 8085 actually looks like. Okay, so now you basically know from the previous tutorial that all the registers, starting from the accumulator to the flag and even all the general purpose registers, are all 8-bit registers. So that's why I'm writing 8 in bracket, okay, beside all of these, and except the stack pointer and program counter, which are 16-bit registers. Now apart from that, if you just take a look at this diagram, I mean this part of the block over here, then you see that there are also two temporary registers. Okay, one is the register W, okay, and the other is the register Z. So both of these are temporary registers and are also 8-bit registers. So that means they hold 8-bit data. Okay, and now the question is, well, we haven't seen these registers anywhere in the previous tutorials, and neither we'd use them. Okay, I'll tell you the truth. We didn't use these registers only because the W and the Z registers, okay, the W and the Z registers are only used internally. Okay, so these are only used internally by the 8085 hardware. Okay, so used internally by 8085 hardware. Okay, I mean hardware mean I'll just explain that over here. By hardware I just mean the embedded hardware. Okay, so I'm referring to all the embedded devices that are present, or rather the embedded circuitries that are present inside the 8085 chip. Okay, so all of them, they, while performing various tasks during a program execution, okay, the W and the Z registers are used. Okay, so they just use them. So this is just used while performing program execution. So I'm just gonna write here during program execution. Okay, just give me a while. Okay, now apart from all these, well, these are the only the two new types of registers we had encountered over here. Now apart from that, we also got one more part of this, or rather two more parts in this particular block, that is the register select logic. So this register select logic block that we've got over here in this register section, okay, it contains a multiplexer as well as a register selector. Alright, so this particular block, I'm just going to elaborate that over here. So the register select block, okay, so this is the register select block that I'm just talking about. Now it consists of two parts. One is a multiplexer, okay, which is, well, not shown in the diagram over here. So one is a multiplexer and the other is a register select, okay, the register selector. Okay, so I'm just gonna write that down over here. Register, sorry, don't mind my mistake, selector. Okay, so these two are basically circuits that are present in this particular block. Okay, that's a register select block. And what happens is that whenever during a program execution, whenever let's say we need to store a data in the register B over here, then we need to, the internal devices that are present inside the 8085 chip, they need to select the register B in order to store the data over there. So at that very moment, this particular register select block comes into action, and over there the multiplexer helps in selecting the proper register, the multiplexer along with the register selector section that we've got over there inside the register select block actually helps in selecting the exact register where the data is to be stored, or maybe data is to be taken or retrieved from the particular register. Okay, so these just help in selecting or accessing the specific registers in this particular block that we've got over here. Okay, and apart from that, we've also got an increment or decrement latch, okay, which is also a 16-bit register and used internally by the 8085. So this increment block that we've got over here below the program counter, that's this one, okay. This increment decrement latch that we got over here is basically a latch. Okay, so I'm just gonna write that down over here. So the increment, okay, just give me a while over there. Okay, so the increment or decrement latch is basically a latching device. So it's basically nothing more than a data latching device. Okay, coupled with, that is just present together with the program counter register, so that it can hold the data. Okay, it can hold the incremented or decremented data. Okay, when the program counter basically increments or decrement, basically it increments itself whenever it needs to maintain the program instruction execution sequence. Okay, so at that very moment the increment decrement latch is actually the most important part along with the program counter. Okay, now the question now that can basically arise in our minds is that, well, we send instructions to the microprocessor and it does the necessary jobs according to the instructions. But how does it understand what each instruction actually means? Okay, now that's a very valid question. Now, in order to answer this, I'm going to introduce you to this instruction register block that I've got over here. Now, actually, this instruction register and decoding block got two parts. One is the instruction register, okay, that's an 8-bit register, okay, and apart from that, we've also have an instruction decoder block, okay, and it also encodes the machine cycle. Okay, now in this very part of, the section, okay, what the instruction register basically does is that whenever an instruction comes, okay, and this part over here represents the internal data bus. Okay, I'm just gonna write that down over here, that this is actually the internal address or data bus. Okay, so this is just present internally within the 8085 microprocessor. So whenever any address or data comes, or rather, let's just refer to it as data, because instructions are data, of course. So whenever the instructions they just come through this particular internal data bus, at that very moment, the instruction register stores this 8-bit data of the instruction. Okay, and then and then it just sends it to the decoder. Okay, that decodes or understands the meaning of the instruction concerned, and thereby the 8085 would understand what it should do upon a certain instruction. Okay, so let's just illustrate a suitable example. Let's say you've entered, or rather, let's say your program contains an instruction, let's say MVI, okay, B, C. Now, using this particular instruction, you want to transfer an 8-bit data from the register C into the register B. Now, how would the 8085 understand? Okay, now whenever you're writing the program, you remember that while entering the program into your trainer kit, okay, you do not write the instructions, or rather, you do not just send the instructions directly, but you just convert them into their hex code. Okay, so if we're talking about the hex code for the MVI B, C instruction, then its corresponding hex code is basically 41. Now, this is basically 41H, okay, because it's a hex number. So now 41H in binary would basically mean 0100 and then 0001. So whenever the 8085, actually the 8085 doesn't understand anything about this particular hex code. It doesn't understand anything about 41H. What it actually understands is this particular binary code. So this binary code is actually what gets things going. Okay, so this is the equivalent binary code for the corresponding hex code of this MVI B, C instruction. So this binary code is actually meaningful to the 8085 microprocessor. So whenever it receives this code, okay, it would activate the corresponding circuits inside itself, okay, and that way it would just execute the process of data transfer from, or rather data copy from the register C into the register B. Okay, so that's how it would execute this particular task. All right, now again, another question can basically pop up in your mind that, well, there are so many parts inside the 8085 and all are working in synchronization with each other. So how is everything so synchronized? Okay, that's a good point. Now here I'm going to introduce you to the timing and control unit, which actually does this work of synchronizing every task inside the 8085 microprocessor. So this timing and control unit has got, well, various control signals, okay, which can be either input or output signals. So first of all, it needs a clock, okay. It basically requires a clock pulse. Now that is just sent by connecting a crystal oscillator at the X1 and X2 input pins, okay. So if we basically connect a crystal oscillator, so we need to connect a crystal oscillator right over here. Okay, now this crystal oscillator, which we connect at the X1 and X2 input pins, okay, it just helps to set up the internal clocking circuit inside the 8085 microprocessor. And we all know, or as we've seen in the previous tutorial, that the clock pulse that its internal circuit would generate would be about 3 megahertz. Okay, now this 3 megahertz clock pulse, so this is actually the clock frequency of the 8085 internal clocking circuit. Now this clock frequency will actually leads to a clock period. Okay, it just leads to a clock period of approximately 0.33 microseconds. Now this clock period is what is actually used in order to synchronize every operation inside the 8085. Okay, so whenever the 8085 receives the clocking signal, okay, whenever the clock is high, then only the tasks get executed, and else it doesn't. So every instruction that you would find in the instruction set of the 8085, you'll see that every instruction consumes an integral number of clock cycles in order to do what it actually does. Okay, so in this timing and control unit, okay, apart from synchronizing every operation, it also got, well, as I said, various control signals. Like for example, it's got the reset in, okay, so which is used in order to reset the entire 8085 microprocessor and clear its program counter. And it's also got a reset out control line, through which we can reset any other externally connected device, okay, to the 8085 microprocessor. And then it has a ready control pin, the ALE, the S0, S1, the input, output, and memory pin over here, which controls the input, output, and memory operations. The read, write, hold, and hold acknowledge pins, all of them that are used to interface with peripheral devices, are all present in the timing and control unit. So by far this is the most important part, okay, in the 8085 after the register section, the ALU, and the instruction decoder and register section. Okay, so without this timing and control unit, none of the tasks inside the 8085 would have proper timing. Okay, and every instruction and every operation inside the 8085 would just become desynchronized otherwise. Okay, all right, so that was quite a lot of explanation. Okay, now apart from that, we can see that in order to connect to the outside world, okay, the 8085, as I said, it got 16 lines or 16 address lines. So here the address buffer, okay, actually interfaces, or rather connects to the higher order address bus, that is the A8 to A15, and there is another address buffer that just connects, or rather address or data buffer, that connects with the lower order address or data bus. And we all know how the address and data bus, that's a lower order address data bus, starting from 80 to 87, is time division multiplexed. Okay, so it can just take the form, or it can just behave as an address bus at one instant, and then it can behave as a data bus. We all know that. Okay, and all these buses, okay, the higher order and the lower order buses, they are all 8-bit buses, and together, and taken together, okay, they form a 16-bit address bus, and that's how the 16-bit address is generated by the 8085 in order to interface to externally connected devices. Okay, now apart from all these, we also have the serial input output control section, okay, which controls the serial input data, and that just consists of the pins serial input data, or SID, and serial output data, or SOD. Now with these sections, the 8085 actually executes the serial input and output operations. Okay, so the serial communication, what takes place using these two pins. So I'm just going to write that down over here. So these are used for serial communication. Okay, and this is quite useful at in certain applications concerned. And we also have the interrupt control section, which consists of flip-flop stages and several interrupt pins. So in all, there are 6 interrupt pins that we can basically see, starting from the trap, which has the highest priority. Then we've got the RST 7.5, 6.5, and 5.5, and finally 2 other interrupt lines. That is the INTR with the least interrupt priority, and another that's the interrupt acknowledge. So this interrupt acknowledge pin is actually useful whenever we accept interrupt. We make the 8085 accept interrupt request through the INTR pin. Okay, so actually we can say that the INTR and the INTA pins, they work in conjunction. Okay, so that's how the interrupting section is, and we had discussed it in the previous tutorials in detail in the tutorial on interrupts, so you can refer to that if you need further information. Okay, now other than that, we also have, as I said, here goes the accumulator. I didn't encircle it. Okay, and there's another temporary register used internally by the 8085, as well as certain flip-flop circuitries that hold data temporarily. Okay, so all these parts taken together, they form what the 8085 microprocessor actually is. And you can see with these arrow marks, okay, wherever you can see that there are arrow marks that have the arrowheads on both directions, they actually are bidirectional lines. So this is such a bidirectional line. Okay, I'm just gonna write that down over here. So this is actually a bidirectional. Okay, this is actually a bidirectional line that we've got over here. So the accumulator, as we know, it needs to send as well as receive data from the common internal address data bus. So that's why it has a bidirectional line connected. Okay, and the data from the accumulator would go into the ALU for processing. So that's why we have this unidirectional arrow mark over here. And data from the temporary registers also goes to the ALU. So we can say that these flip-flop temporary register and the the accumulator as well as the ALU entirely form a single section. So we can refer to the accumulator as a very important part of the ALU, or you can say that the ALU, or the logic unit of the 8085 microprocessor. Okay, so that's how things work around over here. And then we can also see that from the instruction decoding section, okay, whenever any instruction is decoded, then the output is just sent into the timing and control unit, which would synchronize every action on the 8085 chip. Okay, so that every necessary operation could be executed without a glitch. Okay, and we can also see that there is another bidirectional line connecting the register section with the internal address data bus. So is the same present between the serial input-output control and interrupt sections. Okay, and that said, we almost wind up our discussion right over here, where we've just introduced you to the detailed internal architecture of the 8085. I guess you can now make out what happens inside the 8085 and how each part works in synchronism with each other. Okay, so with that, we'll just bid you goodbye from this tutorial here on, and we're gonna see you next in the forthcoming tutorial. So bye bye for now, and see you in the next tutorial.